Our final presentation is from Professor Jiadi Su, Associate Professor of Radiology at Johns Hopkins University School of Medicine. He's going to talk about advanced MRI pulse sequence development, bridging technical innovation with clinical applications in cerebro-cardiovascular medicine.
Okay, good afternoon, everyone. And firstly, of course, thank Kenny for invitation and give me this opportunity to present our work. And today I will show you some advanced MR sequence development in our group. And for the people who are not familiar with the MR, I just give you very short, brief introduction. What's the pulse sequence? Actually, MR pulse sequence is very similar to the sheet music. And as we know, sheet music is a time diagram for playing at the piano. Actually, MR sequence is very similar. Just use a different variety of pulse sequence, pulses and gradients combined together and with different delay to give you the MR scanner instruction how to collect all the MR images to give you different contrast as we wanted. Basically, for most of the MR sequence, we have two different parts. Firstly is the preparation module, and then acquisition module. As shown as here, such as in the commonly used method in our group, is CESS method. So you have recovery time, you have B1 saturation time, and also you have acquisition to give you the MR image, give you the spatial information. Of course, in reality, you can vary the pulse delays in different pulse shape, such as change the pulse from the block pulse to the Gaussian pulse. Actually, even more complicated, you can play the acquisition and the pulse interleavely. So give you see lots of variety and give you many different contrasts. So of course here I just show you two examples how you play with these sequences to generate different contrasts. I just use two examples. One is the tissue CSF water exchange by the MESA method, and another one is also CSF flow in the brain. We call it the velocity selective spin labeling MR. So firstly, why we are so interested in the CSF? Because the CSF was not studied intensely previously, and people thought it's not that critical in the brain. Just use a buffer use a buffer system for the mechanical protection. But recently, the discovery of glymphatic system completely changed the overview of the CSF function in the brain. Now the glymphatic system is a system which is describe the CSF and interstitial flow, CIS flow exchange process, and this process was considered to wash out the waste in the brain. Therefore, it's really critical related to the neurodegenerative diseases. And after discovery of the glymphatic system, the Neuroscience Society have gained lots of interest. Therefore, there are many MR methods developed. But the majority of them really just look at the CSF flow in the ventricle, which is not directly related to the glymphatic system. So therefore, the golden standard for the field study the ISF CSF exchange process is called the intrathecal injection of gadolinium. So in this method, we inject the gadolinium in the spinal cord, and then look at how the gadolinium tracer exchange with the ISF in the brain in the next several hours, even 24 hours, as shown here. But this method is highly invasive, and actually it's not allowed for the health subject in the US. So there's another method which is based on we call the arterial spin labeling approach. In this method, we look at the blood to CSF flow. Of course, this is still not the ISF CSF exchange process. Also, because the blood to CSF flow is a very slow process, therefore the signal is extremely small, and therefore in both methods, really not really ideal for the glymphatic system function assessment. And therefore, we really need a non-invasive method for the glymphatic function assessment. Basically, look at the ISF CSF exchange process. Therefore, we have developed this method called magnesium transfer indirect spin labeling approach. In this approach, again, it's similar. We have two separate modules. One is the preparation module, one is the acquisition module. In the preparation module, as shown here, just a train of RF pulse. Here we use single Gaussian pulses and with some delay, and of course have some offset. And for the acquisition module, we use a 3D TSE readout. It's kind of a readout which can suppress the tissue and tissue and the blood signal, and only look at the CSF in the brain. The acquisition parameters used for the preparation module is we use control is 200 ppm offset, and the label is minus 10 ppm offset. But the peak B1 is 3 Mach Tesla, and the saturation time is 3.7 seconds. So with this method, just show you how it works. Basically, we use the train of pulse to label the semi-solid macromolecules in the tissue. As CSF don't have any protein inside, therefore this RF pulse doesn't affect the CSF signal. Once the labeled semi-solid macromolecules, it will transfer the magnesium to the RSF tissue water, basically RSF water. Then the labeled RSF water begin to flow into the CSF, and will cause the signal reduction in the CSF signal. Here show the typical missile maps on the healthy subject. As you can see, the tissue CSF exchange have occurred almost everywhere in the brain, from the subarachnoid space to ventricle, even to the coral plexus, and so on. The most of the clear signal found in the coral plexus, which is understandable because this is a region which is considered as a region produced CSF. But interesting in the ventricle, although there are many signal water inside, but the tissue CSF exchange is really slow, almost zero. And not only these two parts, also if you look carefully, the perivascular space also have strong tissue CSF exchange, as shown here, especially in the zoomed images. You can see here the PVS, and here's the tissue CSF exchange. You can see very strong signal in the PVS region. The more interestingly, if you look at the signal even in some region that don't have PVS in the long T2 weighted image, we're still able to see them in the missile images. That means this missile method can be used to enhance detection of the PVS, as demonstrated in this zoomed in images. You can see here we cannot see any PVS signal, but here we see strong signal in the missile images, as shown here too. Almost every slide have demonstration that there are no any signal in the long T2 weighted image, but you can see in the missile maps. So once you get the missile maps, you can get the tissue CSF exchange process by using this mathematical model. You can see there's rapid flow around 600 in the PVS, and the coral plexus is also very high, which is reach 300. But for the limbic system, also such as the hippocampus and the cingulate, also has higher exchange rate. Other regions is much smaller. And also this tissue water exchange is really strong age dependence in most regions except the third ventricle and the fourth ventricle. So as shown, one application of this missile method in the tumor model, in tumor patient, here is the gadolinium contrast enhanced image show where the tumor is. Here is the tumor of this patient, and the flare image show the edema region in this subject, and if you look at the flare image, which is the accumulation of edema, and but you cannot see details here. But if you look at the missile maps, you can see they really heterogeneous, and some regions have really high rapid water exchange, and some regions have slower. We expected that with higher signal, that means the edema is forming in this region. Of course, we need further longitudinal study to confirm this. So as I mentioned, this tissue lymphatic system is strongly correlated to the neurodegenerative diseases. So as shown here, actually this work was did by JAMPAS group in Hong Kong University, and they show that in both multiple sclerosis and in the Alzheimer's disease, the both tissue system change dropped dramatically, particularly in the MS, that's 20% drop. And here I show the second example to show how we can mapping the perivascular subarachnoid space with this velocity selective spin labeling approach. PVSAS, the perivascular subarachnoid space, is a new structure actually discovered just last year. What they found is by intrathecal injection of gadolinium, the stone shape was formed in around the artery region in the subarachnoid space. If you show 3D structure, it's more clear. Here you can see many PVSS in the brain, which was thinking to facilitate the transportation of the tracer from the ventricle to in the cortex region. But how to detect this signal is not that simple. And traditionally, the first physical contrast MR was a golden standard to look at how CSF flow in the brain. As shown here, it's show clear, beautiful images. However, you cannot use this one to detect the PVSAS because there are many blood. If you look at the PCMI, the blood signal is super strong, but we already know the PVS is surrounded the blood, also the signal, PVS signal is much slower and weaker. Therefore, you cannot see them in the PVSAS just using PCMR. Therefore, we introduced this velocity selective spin labeling approach. In this approach, we just use a 290-degree pulse and 180-degree pulse in the between, and then we use a bunch of gradient to encode the flow in the brain. And for the control, we just use a different gradient to make them flow insensitive, but they have similar diffusion constant for these two pulse sequence. But in practice, if you use single flow encoding module, the response function is a oscillation shape, which is not really ideal for the flow mapping. Therefore, we repeat the unit 80 times. That's we call the Fourier transform based VSSL. In this method, the response function is more like this kind of shape, which is a more linear function. And I have to mention that this method was traditionally used for the arterial spin labeling study, which is encoding the rapid flow in the blood, and then look at the blood signal flow into the peripheral tissue to look at the peripheral signal. In our study, we use this transit period, which is the velocity is proportional to the VSS signal to look at the flow speed in the PVSAS. So basically use this linear period, and also we use a very long T 3D Grace method to suppress all the blood signal and the tissue signal. And here is the precision module, and here is the image acquisition module as I showed before. Now here the MR parameters we use. And then if you look at the control images, we can see all the CSF signal was visible in the whole brain as we expected. But if we just look at the VSS signal, you can see only the rapid flow region can be seen, such as for those one PVSAS region, and for this part is the canals connect to the third ventricle, fourth ventricle, all the ventricles. That therefore their flow rate is really high. And to confirm what we see really the PVSAS, we overlap the images with the radiography, which is shown in the blood in the red signal, and also we overlap with the T1 weighted image to confirm the region. You can see the PVS signal from the middle cerebral artery, which is the M2 region, and also we can see the from the anterior cerebral artery A3 region. Also, this is M1, and this is posterior cerebral artery. They all confirmed we see what we saw is really PVSS signal. To make it more clear, we show the maximum intensity projection images and compare them with the PVSS got from the intrathecal injection. You can see they're very similar, and also you can see the more the details of the from the PVSS around the small arteries. So here the 3D CS flow patterns, which is show the color show the flow rate, and the you can see you can clearly see the MC, these two MCE and the ACE and also PCE here. So give clear 3D maps of the PVSS in the brain. So here, I think just show two really good examples to show how we can change the sequence, can generate all beautiful images in the MRI. And at last, I'd like to thank all my group members, which is Yihan did most of the work, and also thank all my collaborators, and also collaborating in City University of Hong Kong and the University of Hong Kong and Mount Sinai, and also thank NIH for their continuous support in the past few years, and thank you all for your attention.
Thank you very much, Professor Xu. Now, Professor Yu, would you please present the souvenir to Professor Xu? It's a token of appreciation. Thank you very much for the presentation.